So I will start by writing the classical ELSV formula. ELSV stands for Ekedal, Landau, Shapiro, and Weinstein. Landau, Shapiro, and Weinstein. So it's an equality between Hurwitz's number that I will explain in a moment on the left-hand side, and on the right-hand side you have a combinatorial coefficient and the main part is an integral on the moduli space of stable curves. Here you have the total Chern class of the dual of the Hodge bundle, again I will explain in a moment, and here you have some expression with psi classes. So I will try to briefly recall the meaning of all this so as not to take the whole hour. So I made a little picture of the moduli space. Here it is. So that's this thing is the moduli space here of genus G stable curves with n marked points. As you see, points of this moduli space correspond to stable curves. If you take a point at random, like here, it's going to be a smooth Riemann surface. But then there is a divisor with normal crossings, and points of this divisor corresponds to curves with self-intersections. And then when you have a point on the intersection of this divisor, you have two nodes, one here and one here. Here you have one node, here you have two nodes. So that's the component, this is called the boundary. That's the component of the boundary that corresponds to non-separating nodes. So if you normalize this curve, it stays connected. Here you have a component where if you normalize the curve, it becomes disconnected. There are several components like that. Okay, and now on every curve, you have n marked points, and you can take the cotangent line to the first marked point, for example. You see, this is the cotangent line to the first marked point on each fiber of the universal curve. So the union of all these curves is called the universal curve.
Looks like tangent.
Yes, but I can looks like tangent. Yes, I cannot draw the cotangent line. Again, so as you see now, you have a complex line over each point of the moduli space. So altogether, they form a line bundle that is called L1, because I took the first marked point. And similarly, you can define L2 and so on up to Ln. So you have n line bundles, and their first Chern classes are called the psi classes. So psi I is the first Chern class of Li, and it's in the two cohomology of Mgn bar. And then you also have the Hodge bundle. So that's the Hodge bundle. And that's the space of, so the fibers of this Hodge bundle are spaces of abelian differentials. So if you take, let me call this map pi, for example, and then E is the push forward of omega of the relative cotangent line bundle. So if you take the cotangent line bundle to the fibers, the sections on each fiber are abelian differentials on this fiber. And over each point here you have a dimension G space of abelian differentials. So this is a rank G vector bundle. Vector bundle. And in this formula you have its dual. So this is well known since 2000. Now I'm going to write another very similar formula that is still not proved, so it's a conjecture. Let me push all that. Oh no, yeah. Before that I should explain the Hurwitz numbers. There is also the left-hand side, and that will allow me to make a transition between the two cases. So H GK1KN is the number of ramified coverings of CP1 of a sphere. It's actually the complex structure here is actually not important because it's a topological invariant of CP1 with by a genus G surface. Okay, so this will be CP1. This will be infinity, and here I will fix m more simple branch points. And so the conditions for the ramified coverings that I want to enumerate have n preimages of infinity of orders k1, kn. So the degree of the covering is equal to capital K, which is the sum of the ki's. And then I have as many simple ramification points as needed. I don't know how to draw that, something like that. Right, all these are simple ramification points, and their images are all fixed here in the target. And you can believe me, or you can compute the Euler characteristic and check that m, this number m, should be equal to 2g minus 2 plus n plus k. If you want this surface to be of genus G, that's the number of simple branch points that you have to fix. Okay, so now how do you compute this if you want to actually compute this Hurwitz numbers? Let me first of all introduce a generating series. H of beta and then P1, P2 and so on is going to be the sum over n and G and sum over K1, Kn. Beta to the m divided by m factorial. Hg K1, Kn. Pk1 and so on, Pkn divided by n factorial. So maybe I should make one small comment that this number m here, or the genus, are expressible right there. They give the same information. So I prefer to write the genus here, but the number m here is expressed from the genus. And I could also write m and express g from m. That would be equivalent. Okay. So now I'm going to write an expression for this function in terms of the representations of the symmetric group. Okay, so first of all, let me introduce a notation. P of sigma, if sigma is a permutation, then P of sigma is going to be the product over the cycles of sigma. P sub length of the cycle. So let's say C, length of C. Okay, so if sigma, for example, is equal to 1, 2, 3, 4, 5, 6, 7, 8, P of sigma is going to be P3 times P1 times P2 squared. Okay? So now let's denote by T2 the sum of transpositions in S capital K. So capital K is the degree of this covering, or the sum of the ki's. Okay, and then I claim that e to the power h, so this the exponential of this generating series is 1 over, so it's, okay, sum over k, right? 1 over k factorial e to the power, p of e to the power t2. Sorry, beta times t2. Right, this is the correct formula. So where does this come from? What does it say? So T2 is the sum of all possible transpositions. Here I raise T2 to some power m, right? This thing here is the sum of beta to the m, T2 to the m over m factorial. So I raise the product of all transpositions to the power m. That means that I consider all possible products of m transpositions. And the product of m transpositions is the monodromy, is the product of monodromies here of the covering. If I take the monodromies around these simple branch points, I get transpositions. If I go around all of them one by one, I get a product of m transpositions.
Yeah.
So altogether I'm going to get the transposition of the big cycle like that. Yes?
Notation actually it's not really good. P, you see this T2, it depends on K, yeah? It's in grouping of symmetric group K.
Yes.
And
Yeah, but for every k, yeah, you mean
no, because in 1 over k factorial, then something which doesn't depend on k, yeah. You should maybe put k as some kind of parenthesis.
Here you mean?
In T2, yeah.
Yes,
yeah.
but it's better. It's actually better this way. It's a universal thing for
maybe
every.
on p, yeah, because things depends on k, yeah. It makes no sense.
P of sigma is well defined for any size of sigma actually.
Okay, yeah.
So it's and T2, you're right. So T2 should actually
direct sum of group rings of all symmetric groups.
Yeah. But you're right. T2 actually depends on k, and I could write a k here, but
because
it may be better not to actually. It is what is called a stable conjugacy class. The transposition exists. The sum of transpositions exists for any k. You can take it for any k.
No. See, it's impossible to understand this formula. It's so sum over k, 1 over k factorial, fixed number e, and then multiply by something which doesn't depend on. No, the kind of grammatically this formula doesn't make sense.
Okay. If you prefer a k here, I can put it, but it's.
Yeah, it doesn't make sense because otherwise.
Okay. Right, so once again, I take the product of m transpositions in all possible ways, so for all choices of m transpositions, and then I look at the length of the cycles, of the cycle structure of the permutation that I obtain as the product. And my goal is to obtain the permutation with cycles of length k1, k2, kn, and so on. So if I obtain a permutation like that, this p here will give me pk1 times pk2 times pkn, right? So in front of pk1 times pk2 times pkn, I will have exactly the number of ways of representing a permutation with these lengths of cycles as a product of m transpositions. And this is exactly the way to enumerate ramified coverings. And just one thing that is, I have to take the exponential of the generating function, because when I take this product of transpositions, I don't know if the ramified covering is going to be connected or not. So if I do it like that, I actually obtain the generating series for possibly disconnected ramified coverings. And this is e to the power h.
Is this the Burnside formula?
This is the what?
Burnside?
This one, yeah. Yes. So actually, yeah, I can put I can push this one step further. So this is also equal the sum over k e to the power beta t2 of lambda, so sum over partitions of k, representations of sk actually. Lambda here is a partition of k that represents a representation of sk, times the Schur polynomial of P1 and so on, Pk. So this is a way to compute the power of this element, right? So now I have this T2, it's the sum of all transpositions in Sk. It's actually an element. It's actually an element of the center of the group algebra of Sk, right? It's a linear combination of transpositions, so it's in the group algebra of Sk, and it's actually an element of the center because I take a symmetric thing, the sum of all transpositions. So now how do I raise it to the power m? How do I compute it exponential? The answer is that the nice way to do it is to decompose it into idempotents, into a sum of idempotents. So in this center of the group algebra, it's a commutative semi-simple algebra, which means that it has idempotent elements. So for every representation lambda, there's an element in here that acts by 1 in representation lambda and by 0 in all other representations. And then if I raise it to powers, I get the same elements all over and over again. Right, so in general, if I want to raise an element to a power, I should look at its action in every irreducible representation and raise it to the corresponding power. So T2 of lambda is the action of T2 in representation lambda. Right? It's a central element, so in each irreducible representation it will act just by a scalar. And T2 of lambda is this scalar. And if you know the representation theory of the symmetric group really well, you should know the formula for T2 of lambda. And if you don't know it so well, it's a difficult exercise. So it's 1/2 sum I greater than or equal to 1 lambda I minus I plus 1/2 squared minus I plus 1/2 squared, where lambda is equal to lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3 and so on. So when I have a partition, I represent it by a decreasing sequence or non-increasing sequence of its elements. Then I make this small shift. Instead of every lambda I write lambda I minus I plus 1/2. So that this sequence is now strictly decreasing. And this is more or less a renormalized sum of squares of these shifted coordinates. So you can notice that, well, this sequence actually finishes with an infinite number of zeros, right? There's only a finite number of non-zero elements. After that, they're all zeros. And when lambda I is equal to 0, I just have a difference of two similar terms, of two equal terms. So this is an infinite sum, but actually it has only a finite number of non-zero terms. It is well defined. And morally, if you forget about this part, it's just the sum of squares of these elements. And this is added for it to converge. Okay, so now I go in cycles and think, maybe I will continue here. Okay.
Excuse me, this is just a number?
This is just a number. So that's a function on all possible partitions. All possible partitions of all k. Right? Because the sum of transpositions exists in every Sk, so for any partition of any number, I can look by what scalar the sum of transpositions acts in this irreducible representation. And this is the number that I get. Okay, so now I want to write a more complicated ELSV formula that will depend on a parameter r greater than or equal to 1. So it's an integer. Right, so from now on I fix an integer r greater than or equal to 1, and if r is equal to 1, I will find the usual ELSV formula. So the first thing I do, I will go in the opposite direction. I will start by changing the Hurwitz numbers. So now first I have to define tr plus 1 of lambda. So the recipe is very simple. Everywhere you see 2, you replace it by r plus 1. Almost everywhere. There's this 1/2 that stays 1/2. So 1 over r plus 1, sum for I greater than or equal to 1, lambda I minus I plus 1/2 to the power r plus 1, minus I plus 1/2 to the power r plus 1. Right? This is once again a function on all partitions of all integers. And the question is, does it represent anything? So it actually, well, it's not such a, it is actually a very good function. It represents what is called completed cycles. For example, I will write you just one equality. T3 of lambda, for example, can be decomposed in the following way. 3 plus 1, 1 plus 1/12 times 1. So that means that T3 of lambda is the sum of 3 cycles. Sum of 3 cycles. Plus, so here I have the trivial permutation, but with 2 distinguished elements. So actually, k times k minus 1 over times the trivial permutation. And here I have 1/12 times, once again, the trivial permutation, but with 1 distinguished element. So k over 12 times the identity. So this is again an element in the center of the group algebra. And this element acts in this way in every representation. And there's a similar formula for any r, but it gets more and more complicated. There's an expression for the things that you should put here, but it's not the most beautiful way to see them. So these things are rather mysterious, and this is actually the reason why the formula is still not proved, because you have to find these coefficients in a geometric way, and I still cannot do that. But now once you have these t's, you can define the new generating series for R Hurwitz numbers, H, G, R, K1, Kn. Let me start with, so e to the power H sub R of beta K1, Kn, B1, B2, and so on. Right, exactly by the same formula. Sum over k, 1 over k factorial. Now I have to write the second version, right? So sum over partitions of k, e to the power beta tr plus 1 of lambda times the short polynomial. That gives me a new power series, and if I take its coefficient, B1, B2, and so on, its coefficients are called R spin Hurwitz numbers, K1, Kn. Once again, so here I should write beta to the m divided by m factorial, and here pk1, pkn over n factorial. Right, so now everywhere I have this parameter r. So these are some new numbers.
Something like coverings roughly with sharified r faults.
Yeah, so yeah, roughly. These are coverings, so from a genus G surface to CP1 such that df has an north root. So that means that critical points, right? Critical points are zeros of df. If df has a north root, it means that critical points go by collections of R.
But that's the maximum, or is it everywhere on?
Sorry?
So
All critical points have this L.
Every critical point has, yeah. So, well, it's there are some boundary contributions. So let me draw a picture for T3. So I wrote this equality 3 plus 1 1 plus 1 12 times 1. So now I can draw a picture associated with every term. This thing is just a critical point that behaves like where this map F locally behaves like z cubed. So that's a double critical point. But then I also have a contracted component of genus 0 that is attached to two sheets of the covering. And here I have a contracted component of genus 1 that is attached to one sheet of the covering. So here I have a covering with two distinguished sheets, and they are distinguished because there is actually a genus 0 component that is attached to them. And here I have a covering with one distinguished sheet because there is actually a genus 1 contracted component. So you see, these are actually stable maps. Stable maps can have contracted components. And the image of these contracted components are counted as branch points with some multiplicities. There's a formula that gives you the multiplicity, and the formula gives you 2 in all 3 cases. And these are exactly the 3 possible cases. It's called the branching morphism that extends the notion of multiplicity of a branch point to stable maps. Okay. And so now I can write the corresponding ELSV formula. Yeah, okay, I guess I'll have to erase this, but it's very similar. So H, G, R, K1, Kn is equal to m factorial, and this time m is 2g minus 2 plus n plus k divided by r. So as I said, the critical points now go by collections of r, so the number of different branch points is divided by r compared to the previous, to the ordinary case. Now there is a power of a here that I never remember by heart. M plus n plus 2g. M plus n plus 2g minus 2. Sorry, there is also the combinatorial factor ki over r to the power pi over pi factorial. So I'll explain the notation. And here I have what is called the space of R-spin structures. So once again I will explain what it is. Here is minus R star B push forward of L. Now there are some new things, but okay. So that's the formula. Now once again I have to explain all the letters. Okay, so first of all, there are these numbers k1, kn that correspond to the branching at infinity, and I have to write each of them. I have to divide each of them by r and write the quotient and the remainder. It's going to be r pi plus r minus 1 minus ai. So that's the quotient, and that's the remainder that for historical reasons has to be reversed. Instead of going from 0 to r minus 1, you go from r minus 1 to 0. Right, so from each number ki, you get the number pi and the number ai automatically. And this already explains the combinatorial factor here and the indices that are here, but I still have to explain what this space is. And the space mg 1 over r a1 an is the space of, so it's stable curves of genus G with n marked points and with a line bundle such that its rth power is isomorphic to, is identified with the cotangent line bundle twisted by sum of minus ai xi. So this thing is called an R-spin structure. Once again, an R-spin structure is an rth tensor root of the cotangent line bundle. So here I have the cotangent line bundle. I twisted by some divisor supported on the marked points, and then I take the rth root. And so the first term class of this, let's say the first term class of this line bundle is 2g minus 2 minus sum of the i's, and it should be divisible by r. Otherwise it doesn't work. Right? If you want to extract an r tensor root, it has to be divisible by r. And that's the same condition as this. Right here, in order to get an integer m, you also have a condition of divisibility by r. It's actually the same condition. So the integral is well defined if and only if this m is integer, and that's the situation where the Hurwitz number exists to begin with. So why do I look at this space? That's once again. So if you look at this, explanation, when you have a ramified covering like that, right? So it has poles. F has poles. Let me write it here. One moment. F has poles of order ki at xi. Right? It has m poles, so I call these poles x1, xn. So F has a pole of order ki at xi. So df has a pole of order ki plus 1. Right? At xi. And this is equal to r times pi plus 1 minus ai, right? If I rewrite ki like that, I obtain r times pi plus another r. There's a plus 1 that kills this minus 1, so I just have a minus ai. Right? And that means that if I take a square root, an rth root of df, it will has a pole of order pi plus 1. And this is the thing that I have to twist the cotangent line bundle with in order for this to be divisible by r. Right? If I want this to be divisible by r, I have to, at the beginning it's not, so I have to twist the line bundle by this minus ai times xi, and then the pole will be of order r times pi plus 1, and I will be able to extract the rth root. Okay. And so now I have to explain one last thing. That's the this thing in the numerator. And this thing is the numerator is as follows. So here I have my moduli space of R-spin structures. Over this moduli space I have the universal curve, and I also have, let's call this pi as before, and I also have the universal R-spin structure. Since this is the space of R-spin structures, it means that on the universal curve I have the universal R-spin structure. So here I have a line bundle on each fiber, and the union of these line bundles gives me a line bundle over the whole universal curve, and its rth power is the cotangent line bundle to the fibers. And now I can look at the push forward, so the sheaf of sections of this line bundle, and take its push forward, the push forward is this R star, so the derived functor. So more or less on each curve I can take H0 of CL and H1 of CL, and the formal difference H0 minus H1 glues into two sheaves that are called R0 P star of L and R1 P star of L. Right. This is for one curve, and this is if I do it on the whole moduli space. I obtain two sheaves. And so R star P star of L is equal to R0 P star of L minus R1 P star of L. It's a rather common construction. This is what you see in the Grothendieck-Riemann-Roch formula, for example. And you can check that in the case of R equal 1, if R equals 1, you obtain here exactly you obtain actually minus the Hodge bundle. So here you obtain the Chern class of the dual of the Hodge bundle, exactly as you should. Because if R is equal to 1, this L here is just the cotangent line bundle. So its H0 is the Hodge bundle, and its H1 is the trivial line bundle C. So it has no Chern class. Okay. So I would like to make one remark on this R-spin Hurwitz numbers before I continue. Should be. That's in order to make them more attractive. So these expressions here, these TR plus 1 of lambda, I learned them from a paper by Okunkov and Pandaripande, where they compute Gromov-Witten invariance of curves. So it actually turns out that this thing is related to the class psi to the power r. And I can write concrete equality. So this Hurwitz number Hg r k1 kn is equal to a Gromov-Witten invariant. So if I take the space of the space of maps to CP1 relative to infinity of degree k, and the branching at infinity, so if it's relative to infinity, it means that I have to prescribe a ramification profile at infinity. The ramification profile is prescribed by k1, kn. So that's a space of relative stable maps. It has a virtual fundamental class. And I can, and I should add m marked points here. marked points. Marked points, and k is the degree of the map. Degree. So now I have m more marked points, and I can write r factorial psi 1 to the power r times and so on times r factorial psi m, psi 1 to the power r times the pulled back by the evaluation map of a point. That's the block. And same thing, r factorial psi m to the power r, the pullback of the class of a point by the evaluation map. So I have m marked points, I fix their images because every time I take the pullback of a point by the evaluation map. And after fixing their images, I also put rth powers of psi class on each of them. And this will be exactly equal to this Hurwitz number, R-spin Hurwitz number. And again, the relation between the two is not clear. So I mean, this thing is proved. This is proved by Oklinkov and Bunderich-Lande. But it's not clear why it should be related to integrals on the space of R-spin structures. So if you prefer, you can reformulate the ELSV formula by replacing this number here by this Gromov-Witten invariant. Okay, so now finally I come to the topological recursion.
Excuse me, can you repeat the connection between the
Yes.
two formulas?
Yes, so this formula is proved. So this is the R-spin Hurwitz number that I defined using this completed the representation theory, and this is a Gromov-Witten invariant, right? And this formula is a conjecture, so I should maybe write an exclamation mark here and a question mark here. Otherwise, it's not. Right? So since you know that these numbers are equal, you can take this number and put it here, and you get an equivalent conjecture. And in this way, you have an equality between two integrals. One is the integral on the space of relative stable maps with some powers of psi classes, and here you have a space on the an integral in the space of R-spin structures. And it's not clear why they're equal to each other. It seems like there's a connection between the virtual fundamental classes hiding somewhere, but I don't know. Okay. So the relation with the topological recursion. There are more properties of the Hurwitz numbers. So the first property is called the Bouchard-Marigne conjecture. That was actually proved since, which says that the curve, the plane curve x equals log y minus y is the spectral curve. For Hurwitz numbers. So more precisely, if I write H, G, N, right, maybe I should write W, G, N. Of x1, xn equals sum over k1, kn, 1 over n factorial, e to the power sum of the ki xi, and the Hurwitz number, gk1, kn. and also I forgot the e to the beta to the m over m factorial. So here I also should sum over, no, yeah, okay. And again, m here is expressed from this genus. So maybe, no, sorry, so then, sorry. You probably don't need it here because there is just one m. Once you fix, no. Okay. Once again, beta to the m over m factorial. Okay. So these things here, well, these are functions, but you can transform them into differential forms by differentiating once with respect to each xi. And then what you obtain are the invariants, the topological recursion invariants for this spectral curve. So it was a conjecture for some time, and then it was proved from the ELSV formula. And there's a similar conjecture for these R-spin Hurwitz numbers. The R Bouchard-Marigny that says that the curve x equals log y minus y to the r is the spectral curve. If the spectral curve for R-spin Hurwitz numbers. Hurwitz numbers. And once again, this is still open. So the only theorem I can boast of today is that these two conjectures are equivalent. So that's the main theorem of the talk, is that the R-ELSV conjecture and the R-Bouchard-Marigny formula are equivalent to each other. So if someone proves one of them, both will be proved at the same time. Maybe I should write that down since that's the main theorem. Right, let me write it here. R-ELSV is equivalent to R Bouchard-Marigny. Okay. Yeah, I still have a couple of minutes, right? So I'll try to explain a little bit how the equivalence is proved. So just to make sure you understand, right, once you have the spectral curve, there's the topological recursion procedure that allows you to compute everything, to compute all the Hurwitz numbers, right, one by one. And the ELSV formula also allows you to do that if you can compute some integrals on the moduli space. So in principle, both determine the Hurwitz numbers uniquely, and you can prove that. Well, we can prove that that's the. It's the same. It gives the same numbers. Yeah, that's. I should also write that's joint with Luke Spitz and Sergei Shadrin. Okay, so how does the proof work? First of all, you have to look at the numerators of these formulas. In the ELSV formula, you have the dual of the Hodge bundle, and in the R-ELSV formula, you have this, the Chern class of the push minus the push forward of the spinor bundle. So these things are actually semi-simple cohomological field theories. I'm not going to tell you what that means, but the important thing is that semi-simple cohomological field theories are classified, and they are determined by one matrix valued power series. So completely described by a matrix valued power series. Matrix valued power series. It's the Giventhal R matrix. So the power series for the first one, here you have matrices 1 by 1, so it's actually just one power series. It corresponds to the exponential of minus sum of the k greater than or equal to 1, bk plus 1 over k plus 1, t to the k. So that's the Bernoulli number. So actually, one term out of 2 is equal to 0 because the Bernoulli number vanish, the odd Bernoulli number vanish. So I'm not going to describe you completely the classification of cohomological field theories. It would take too long. But I will show you how, in this particular case, what this formula, what this power series tells us about the Chern class of the Hodge bundle. So there is an expression called the Mumford formula. Mumford's formula obtained by applying the Grothendieck-Riemann-Roch formula to the universal curve, and it gives us the Chern character, the Chern class, of the dual to the Hodge bundle. So it's exponential sum, so minus sum k greater than or equal to 1, bk plus 1 over k times k plus 1, I'll write it like that, times the class kappa k minus sum from for I from 1 to n psi I to the power k, and plus 1/2 delta. Delta is the boundary, and here I have psi 1 to the k plus psi double prime to the k divided by psi prime plus psi double prime. So when you have a boundary stratum like that, you have two psi classes at the node. At the node you have two branches that meet, so you have two cotangent lines to the branches. So you have two extra psi classes. You have, as usual, the usual psi classes attached to the marked points, with the cotangent line to the marked points here. But on this boundary divisor, you also have the cotangent lines to the attachment points of the two branches. So you have also two extra psi classes, psi prime and psi double prime. And here's the expression. So as you see, you can see the power series that appears in front of some expression of classes on the moduli spaces, on the moduli space. And there's a similar formula I have to stop in like 5 minutes, right? Yeah. Okay. So let me. So for the R spin, for the space of R spin structures, you have this C of minus R star of the push forward of L, And this corresponds to a matrix valued power series, and the matrix is R times R. And the elements here are B k plus 1, so it's, let's say, sum over k, again 1 over k plus 1, and here have bk of bk plus 1, 1 over r, and so on, bk plus 1, r over r. Let me write one more term, bk plus 1, 2 over r. So it's a diagonal matrix. And here have the Bernoulli polynomials, and you take the values of the Bernoulli polynomials at the rational points with the denominator r. So once again, you see that if you take r equals 1, you just get this term, which is exactly the Bernoulli number, the value of the Bernoulli polynomial at the point 1. And this is translated by a formula by Alessandro Chiodo for the Chern character of this. So that's equal to the exponential of the sum, again, minus sum over k, 1 over k plus 1, bk plus 1 of 1 over r times kappa k, minus sum from 1 to n, bk plus 1, ai plus 1 over r psi I to the power k, plus 1/2, yeah, I don't know if I want to write the boundary term, that's actually r over 2. Okay, let me write it down, but maybe it's not so sum from a from 0 to r minus 1, delta a. There are actually different types of boundary divisors in the space of R-spin structures that are indexed by remainders modulo r. I think is not so important now. Psi prime plus psi double prime, and here bk plus 1, a plus 1 over r, psi prime to the power k, minus, bk plus 1, r minus a minus 1 over r, c double prime to the power k. Okay, it's too long, and then I have to close both brackets. So once again, you can see all the elements of this matrix appearing in different combinations. And okay, yeah, I wanted to compute one integral, but I think I have to stop here. But what the so Bertrand already mentioned the result that the topological recursion and the classification was actually included inside it, the classification of semisimple cohomological field theories by these R matrices. So when you have this R matrix, when you have a curve, you have remember the B of z prime, or what, z1, z2, that was part of the spectral curve. And then you should take its power series expansions at the critical points and take the Laplace transform, and that gives you this matrix valued power series. That classifies cohomological field theories. So there's actually a connection between these power series here, this one and this one, and the expansion into power series of this two form, dz1, dz2 over z1 minus z2, expanded in coordinate y. Right? if you have a rational curve, you can take Z squared. If you have a rational curve, you have this two form, and you can expand it into local coordinates in the neighborhood of critical points. And the coefficients of this expansion should match the coefficients of this power series after the Laplace transform. And so the Laplace transform is some integral, right? The Laplace transform of f is something like that, dz. And this integral, when you write it for this spectral curve, this integral happens to give you the inverse of the gamma function, more or less. Actually, 1 over the gamma function. And I don't know if you know that, but these power series, both these and this here, they actually asymptotic expansions of the gamma function.
Stirling formula.
The Stirling formula, exactly. The Stirling formula is the leading term. Gamma of t is equivalent, right, to square root of 2 pi t, t to the power t minus 1, e to the t, times the exponential of this thing, but with a plus sign. So when you have 1 over the gamma function, and these actually things appear in front of the integral, so they simplify. And in the end, you get exactly this power series, the power series that you want. So the connection between the ELSV formula, or the RLSV formula, and the spectral curve is that when you compute some integrals at the neighborhood of branch points of this curve, you get the reciprocal of the gamma function, whose asymptotic expansion is given by these power series here and here. And I think I have to stop here.
Thank you.